Okay, students, today we'll go through the fundamental theorem of arithmetic of first chapter, mathematics real number. What is fundamental theorem of arithmetic? That is, every whole number is either prime or can be expressed as the product of prime, irrespective its order. This is unique for the number, or we can say every composite number can be expressed as a product of primes, and this prime factorization is unique apart from the order. Suppose 2 is a prime, 3 is a prime. Similarly, 4 can be expressed in the product of prime, that is 2 into 2. 5, that is prime. 6 can be expressed in the product of 2 into 3, that means 6 is composite, 4 is composite, and they can be expressed in the product of prime numbers. Okay, and this product is unique for this irrespective of their order. Let us see one example. Suppose I wrote here 18. So the prime factorization of 18 is 2 into 3 into 3, or I can write it 2 into 3 to the power 2. So this is the prime factorization of 18, and I can write it 3 to the power 2 into 2. That is the irrespective of their order. This. Okay. But in every time when you got the prime factorization of 18, we have to get 2 3s and 1 2s. That is 3 into 3 into 2. This only. This is the uniqueness. Here also 2 3s and 1 2. Here also 2 3 and 1 2, irrespective of their order. That means here 2 into 3 into 3, here 3 into 3 into 2, or we can write it 3 into 2 into 3. But this is unique. This factorization is unique. That means 18 can only be expressed in the form of 3 square into 2. No other numbers can be expressed in the form of 3 square into 2. Okay, similarly I can take another example of suppose 28. We can write 28 as 2 into 2 into 7, that is 2 square into 7 to the power 1. This is for 28, and same thing I can write it 7 into 2 into 2. Yes, it is also correct, because 7 to 14 to 28. I can write also 2 into 7 into 2. This is also correct, and each factorization will get there are 2 2's and 1 7. Here also 2 2's 1 7. Here is also 2 2's 1 7. That means this is unique for 28. That means this factorization is unique for a single number. That means every composite number can be expressed in the product of prime. That means in earlier classes you have read it as prime factorization. Okay, so now where we are using these things. This prime factorization is used to find out HCF or GCD, greatest common divisor, and LCM. Okay, so to find out, suppose application of fundamental theorem of arithmetic, that is, it is used to find HCF and LCM. Okay, it is used to find HCF and LCM. How? And how? By using this fundamental theorem of arithmetic, we have to find out HCF. Suppose we have to find out HCF of 26 and 91. Okay, first of all, I have to write prime factorization of 26 is equal to 13 into 2. Okay, we can write 13 into 2, which we can write 2 to the power 1 into 13 to the power 1. Then similarly, prime factorization of 91, that is 13 into 7, that is 7 to the power 1 into 13 to the power 1. And here, if we have to find out HCF, HCF means, see here, how to find out the HCF. For HCF, product of the smallest power of each common prime factor in the number. So here, see the product of the smallest power. Smallest power means, suppose here is the common is 13, here is 13, and they have same power in each case, so the same power would be taken. So HCF. And here 7 is 1, but here 7 is 0 times. Here 2 is 1, here 2 is 0 times. So we have to take in the smallest power. Smallest power means 7 to the power 0, that is 1. 2 to the power 0, that is also 1. So no need to write this. So HCF is 13. And LCM. LCM, what do you mean by LCM? See there, LCM, how to find out. For LCM, product of the greatest power of each prime factor involved in the numbers. See there, how can you write this? Product of the greatest power. Now, if you see there, 2, so for this LCM, 2 to the power 1, here 2 to the power 0, that means we have to take greatest power. Then 13 to the power 1, here 13 to the power 1, same will taken. Then here 7 to the power 1, here 7 to the power 1, that means the greatest is 7. So we can write this as 182. So in this way, we have to find out the HCF and LCM of some numbers. Okay. Next, what are the we have to solve one question. Okay, suppose you have to write question 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. We have to show this as a composite number, as a composite number. What do you mean by composite number? The number which have more than 2 factors. The number which have more than 2 factors, that means, and the prime number is the number which have only 2 factors. The factors are the number itself and the 1. So here we have to express this as a composite number. So what I did, so I take this as 1, this, because they are the multiplication symbol. So I write it again, 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5, and I wrote it, here is 5 and here is also 5. So from this I can take 5 as common. So when I take 5 as common, so here remains 7 into 6 into 4 into 3 into 2 into 1 plus here is 1, because 5 is taken as common. So now here it has a factor, because I can write it 5 into this, that means factor is 5 and 1 and the number itself, the number itself, hence it is a composite number. Okay, so in this way we have to solve this type of questions. Now one more question is there. Suppose check whether whether 4 to the power n can end with 0 if it has can end with 0 at one's place for any natural number n. Check whether 4 to the power n can end with digit 0 for any natural number. So here first of all we have a concept that if a number is end with 0, that means it has a factor 2 as well as 5, both has a factor. So here we have to factorize 4 to the power n. So 4 is factorized as 2 into 2. That means here we can write 4 to the power n is equal to 2 into 2 to the power n. So a number should have factors both 2 and 5, then it is divisible by 10 and with digit 0. So it has 2 as a factor, but no 5. It has no 5, so this does not. This means 4 to the power n does not end with digit 0. Okay, next, relation between SCF, LCM and product of two numbers, that is number 1 into number 2. So we know that HCF into LCM is equal to product of the numbers, that means two numbers, that is number 1 into number 2. Okay, from here we can solve, like suppose find HCF. if the the two numbers are given and HCF is given, then LCM is equal to product of the numbers by HCF, and similarly HCF is equal to product of the numbers by LCM. So in this way we can get it. Okay, then come to the irrational number. Irrational number. So you know that the numbers which cannot be expressed in the form of P by Q, okay, cannot express, okay, cannot express in the form of P by Q. Okay, if a number cannot be expressed in the form of P by Q, where Q is not equal to 0 and P, Q are co-prime, then we can say these numbers are irrational number. P and Q are co-primes. Okay, then we can say these numbers are irrational. So in theorem 1.3, what is the theorem? Tell about this. See the theorem. Theorem 1.3, let P be a prime number if P divides a square, then P divides a where a is a positive integer. Okay, so see there, let P be a, this is the uniqueness of fundamental theorem of arithmetic. First of all, I want to clear a doubt, that is the, see there, if a number P divides A, then it also divide any of its power, that means a to the power n. Okay, that means same, the vice versa, if a to the power n is divisible by P, then a also divisible by P. Okay, this is the main thing which 1.3 theorem tells about, that is the, if a number P divides A, then it also divides, this is the theorem, if an is divisible by P, then A also divisible by P. Suppose a number, because you know that, suppose whatever the, suppose I have to write 18, this is 18, then what is the prime factor of 18? Prime factor of 18 is 2 into 3 into 3, that means 2 into 3 square. This is the prime factor of 18. And if you take prime factor of 18 square, that also 2 into 3, there is 2 square into 3 fourth, this, that means it has same primes, it primes. If we take 18 to the power 3, then it is also 2 to the power 3 and 3 to the power 6. The same prime factors are there, irrespective their power. We cannot say the power is same. But if we take 18, then 18 square, then 18 cube, then 18 4, then 18 to the power n, then they also have the same prime numbers. I'm not saying about their powers. Okay, they are formed by the product of same prime numbers. They may be repeated again and here. 2 and 3, this 18, we obtain 18 as the product of 2 and 3, that means 2 1 times and 3 2 times, and 18 square also as the product of 2 2 times and 3 4 times, and 18 cube as a product of 2 3 times and 3 6 times. That means the same prime numbers, here 2 and 3, here 2 and 3, here 2 and 3. This indicates this theorem. Okay, so this is all about the theorem 1.3, which which is proved from the fundamental theorem of arithmetic, uniqueness of fundamental theorem of arithmetic. Okay, then we have to prove theorem 1.4. What is 1.4? Prove that this is 1.4. Prove that root 2 is irrational. Root 2 is irrational. So prove. How can you prove this root 2 is irrational? Okay, sorry, irrational. So first of all, we have to prove this from contradiction rule. What is the contradiction? That you have to assume something, then later our assumption will be wrong, then it is proved. So first of all, let root 2 is rational. Rational means that can be expressed in the form of p by q. That means we can say root 2 is equal to p by q, where p and q are co-prime. P and Q are co-prime means what do you mean by co-primes? Actually, co-prime means that is the they don't have any common factors other than 1. P and Q. That means it is not necessary P is prime and Q is prime. Both are prime. No. It may be both are prime. If both are prime, they are also co-prime. But co-prime means they have the HCF 1, or that means they don't have any common factors. Okay, P and Q are co-prime. That means P and Q, the HCF and of P and Q are 1. Okay, then root 2 is equal to P by Q. Okay, now if I squaring both sides, root 2 square, we can get P by Q square, and squaring both sides. Now imply that we can write it p square by q square is equal to root 2 square is 2. Then we can write it p square is equal to 2q square. Here p square is equal to 2q square. That means p square has a factor 2. 2q square means p square has a factor 2. That means p square is divisible by 2 or has a factor 2. P square is divisible by 2. That means P is also divisible. Now study it. P is also divisible by 2. If P is divisible by 2, that means what is the standard? If something is divisible by 2, that means we can write it there is 2. So let P can be written as 2m. Suppose P is written as 2m, that is P is divisible by 2. Suppose P is equal to 2m, and we put this here. Okay, so that means suppose this is 1, and this is the statement. Okay, this is the statement. Okay, then let P is equal to, we have to put it in the 1. That means we can write P square is equal to 2q square. That means in place of P we have to put it 2m square is equal to 2q square. Okay, then imply that 4m square is equal to 2q square, and we got it. That will be q square is equal to 2m square. That means here also 2 is a factor. 2 is a factor of q square. So 2 is also a factor of q. This is the statement. This is statement 1. Okay, let it be. It is statement 1, and it is statement 2. From statement 1 and statement 2. Here p is divisible by 2 and q also divisible by 2. Factor of 2 means q also divisible by 2. That means p, q have a common factor. From statement p and q have a common factor as 2. Hence that means, but here we wrote p and q are co-prime, that means they don't have any common factor, but here it is we get p, q has a common factor 2. That means it contradicts our assumption. Whatever we take, suppose let root 2 is rational, that is our assumption, but here it contradicts our assumption. Hence root 2 is irrational. Hence root 2 is irrational. Okay. Next is the decimal expansion. You read it. The decimal expansion of real numbers, you read it. That is the terminating. This is terminating, and under terminating all it comes all rational number. Then another is non-terminating. NT means non-terminating. Okay, non-terminating are two types. One is non-terminating repeating, and another is non-terminating non-repeating or non-recurring. So non-terminating repeating or recurring is also rational. So how can you know that is two? Suppose here one rational number is terminating, here also rational number is non-terminating repeating, but how can you know? Okay, how can you know this rational number is terminating or this rational number is non-terminating? Okay, so first of all, to know this, you have to go there. Listen, a terminating decimal in 1.6, in theorem 1.6, you have read it. In suppose a rational number p by q is terminating if prime factor, pf means prime factor of q means the denominator, q is the denominator. The prime factor of q is expressed. How it is expressed? Expressed in the form of 2m into 5n, or only 2m or only 5m. That means we can say, simply we can say, p by q means it is the standard form of rational numbers. Okay, a rational number is terminating if the denominator has the factors only 2 or only 5 or 2 and 5. Suppose here, suppose p by q, and I wrote it p by, in place of q I wrote it, suppose 5 to the power m. That means it is terminating. It is terminating because it has 5 to the power m. Suppose similarly we can write, suppose p by q, p by 2 to the power n, here also terminating, this is also terminating. And again suppose p by q, I can write it 2 to the power m into 5 to the power n, then also terminating. Okay, then also it terminating. But if any other factors along with 2 and 5 is there, then it will not terminating, it is non-terminating. Okay, understood? So you have to do like this. So then similarly, a rational number p by q is non-terminating if prime factor of q is not expressed in the form of this. Same thing if it is non-terminating. Okay, so students, this is all about the decimal expansions of rational numbers. And one more thing I want to add here, carefully listen. Okay, suppose 17, suppose I wrote it 3 by 8. Is it terminating? Yes, because 3 to the power, suppose 2 to the power q, we can write it 8 as 2 to the power q. That means it has only 2 to the power. Here I wrote it, that is if it has in this form 2 to the power m and 5 to the power n, or 2 to the power n or 5 to the power m. Okay, so that is where here I forgot to wrote m, here n. M and n are whole numbers or positive integers, whole numbers. Okay, or positive integers. Okay, that means 3 to the power 3 by 2 to the power 3 is terminating, because it is terminating. But if someone asks you, that is how, that means if it is terminating, then how many decimal places have there without dividing it, actually division, without dividing it, how can you find how many decimal numbers are there? So students, you have to do like this as 3 2 to the power 3 into 5 to the power 0. Okay, that is 5 to the power 0. I can write it, because 5 to the power 1, again same thing will happen. But see there, how many places are there? That is the, if suppose 1 q is equal to 2 to the power n and 5 to the power n, we express it. Then if m is greater than n, then m decimal places, m decimal places it have. And if n is greater than m, which is greater, then n decimal places. After n places, that means after n decimal places it will terminate. See there, I will do it. See here, 2 to the power 3, 5 to the power 0. That means suppose m, here n, m is greater than n, here m is equal to 3, n is equal to 0. That means m is greater than n. If m is m decimal places means 3, that means 3 by 8 has 3 decimal places. That means after 3 decimal places it will terminate. So let's check it out. 3 by 8 decimal 30, 8 2 jar, sorry 3 jar 24, then 6 60, 8 7 jar 56, then 4 40, 8 5 jar. So it has 3 decimal places or not. So in this way you have to find out the decimal expansions of rational numbers. Okay students, thank you.